Good morning, everyone. How are you all? All right, fine. So we are going to start this corollary for this Liouville theorem. What is the Liouville theorem? That is, an entire bounded function that must be a constant, right? There is a remark on real numbers. There is no real number or there is no real variable analog to Liouville's theorem. What does this mean? For example, I am having a function sin x where x is your real number. So this function isn't real. So this function is real, and which is sin x. This is entire function. What is entire function? Which is everywhere differentiable and bounded function. In case of real, but it is not constant. And if you view in your complex plane, the same function sin z, cos z, these are unbounded functions in complex plane, right? So this is just the difference. There is a theorem. A non-constant entire function comes arbitrarily close to every complex number. So it is given that we are having an entire function and which is also a non-constant. That entire function comes arbitrarily close, means that function tends to every complex number, right? Now, what does this mean, comes arbitrarily close to? How we write this? That means if you are having any function fz, this is your entire function, a non-constant one, and arbitrarily close to every complex number means we have to show that this function, the difference for this function with this a, let a be your complex number, this difference should be less than epsilon for every epsilon positive, right? So we prove this result with a contradiction. We just take this mod to be greater than or equal to epsilon. We just suppose this and we contradict this result, okay? So let's start with the proof. I'm having a function that is, let fz be non-constant entire function. Alright, I suppose this. If possible, suppose there exists a complex number, say a, such that mod for the difference fz minus a, this is greater than or equal to epsilon for all z, for some positive epsilon, right? Okay. Now we suppose another function, let's say then the function gz. I'm taking this function to be equal to the reciprocal for this mod, 1 over fz minus a. Alright. Is this function entire? See, your fz is an entire function. Obviously, gz is also an entire function. So this is entire function. Alright. Taking the mod on both the sides, let's see. Also, if we look at the mod of gz, what is that? This is equal to 1 over mod of fz minus a. If mod of fz minus a is greater than or equal to epsilon, then its reciprocal will be less than or equal to epsilon. Now, mod of some function comes out to be less than or equal to some number. That means this function gz is bounded because it is less than or equal to some number. Its mod is less than or equal to some real. So this is bounded function, right? So since gz is now become entire, it is also entire function and also a bounded function. So it is entire bounded function. What can we say now about gz? Just remember your Liouville's theorem. What the theorem says that entire bounded function must be constant. So if gz is entire bounded function, then gz is constant, right? So let's write this. By Liouville's theorem, gz is constant. That means, what is gz? The value for gz is, we know that if gz is 1 over fz minus a we have taken, then 1 over gz will be fz minus a. If gz is constant, then 1 by gz is also a constant. That means fz minus a is constant, which implies, what is fz then? Take a to the other side. This will be equal to 1 over gz plus a. This is constant. Oh, your function comes out to be a constant 1. But in the theorem it is given that fz is non-constant entire function. So this is just your contradiction now. So fz is constant, which is a contradiction. Our supposition was wrong. So thus, every non-constant function entire function, that means this function comes arbitrarily close to every complex number. Easy? Simple? Alright. Finish. Now a corollary for this. Suppose fz is a non-constant entire function and you have given any complex number a, then there exists a sequence zn such that f of zn tends to a. Now we are having a sequence z1, z2, z3, so on, not having only fz, we are having the sequence, and that f of zn tends to a. So now what we are going to claim? We are going to claim that for each positive integer n, there exists a point zn such that f of zn minus a, now this mod will be less than 1 by n. We have to claim this thing. Then only f of zn tends to a, if n supposed to be n tends to infinity, right? Now n is your any positive integer. If you put n equal to 1, 2, 3, 4, any number if you put, then this will tend to 0, 0.1, 0.2, 0.001, 0.031, whatever it may be. So this value, the function f of zn will tends to a if this mod is less than 1 over n, right? For n tending to infinity, because we have given a sequence. So just we also do this result by the contradiction. So we just suppose the opposite one and just contradict this result. What we will suppose now? If possible, suppose that mod is greater than equal to 1 by n. Instead of less than, let for any positive n it is greater than equal to. So let's start with the opposite. If possible, suppose that there exists a positive, I'm taking that integer to be capital N, such that this mod f of z minus a is greater than equal to 1 over n for all z, right? Then again we have to suppose that function gz, the same result is going to be done. Then the function gz is equal to 1 over fz minus a is entire. Fine. Also now let's take the mod of gz. Sorry, it happens. Mod of gz is equal to 1 over mod of fz minus a. Now this reciprocated mod with this will be less than equal to 1 by n. Alright, for all z. Now since this mod is less than equal to some number, so this will be your bounded function. So therefore gz is entire bounded function. So by Liouville's theorem, this gz is constant. So if gz is constant, then 1 over gz is also constant. And what is that? 1 by gz is fz minus a, right? Because since gz is 1 over fz minus a, so 1 over gz will be fz minus a only. So this is also constant, which implies taking fz at one side, taking a to the other side. This function is constant. Oops, again fz comes out to be a constant function, which is a contradiction, right? That means our supposition was wrong. So therefore our supposition was wrong. Thus for each positive integer there exists a point. Now I'm taking Zn because this is for each positive integer, okay? So I just write Zn now, such that mod of f of Zn minus a, this should be less than 1 over n, right? This is only we have to claim. Alright, letting n tends to infinity now. N tends to infinity, we get limit n tends to infinity mod of f of Zn minus a. This will be less than equal to 0. Good. Which implies this limit n tends to infinity mod of f of Zn minus a is equal to 0. Now either it is less than 0 or equal to 0. So this is equal to 0 because it's a mod. So limit n tends to infinity. If mod is equal to 0, then this f of Zn itself minus a, this is also equal to 0, which implies limit n tends to infinity f of Zn tends to a, or it is equal to a first. This is equal to a, hence f of Zn comes arbitrarily close to every complex number a, right? Done. Easy. Next, there is a remark which is very important one. Now we are saying that every non-constant entire function comes arbitrarily close to any complex number, right? We are saying this. We have also proved this result just now. So there is a remark which says that though a non-constant entire function comes arbitrarily close to every complex value, it does not necessarily assumes every complex value actually. Now every complex value, is 0 is a complex number? Yes, 0 is also a complex value. Now if you are having a function fz to be equal to e the power z, no doubt this function is non-constant entire function. But can this function comes arbitrarily close to 0? Yes, but this number cannot be equal to 0. This e the power z can never be equal to 0. Liouville's theorem says that every bounded entire function must be a constant. But here we are having a theorem that a non-constant entire function comes arbitrarily close to every complex value. Now if we are having this function e the power z, which is a non-constant entire function, that means this function must come close to every complex value. But if you look at this function f of z, now this function cannot be equal to 0. This can never be equal to 0. If you put z equal to 0, this value comes 1. If you put z equal to 1, this value comes e. So there is no value of z for which this function comes out to be equal to 0. Right? However, if you having instead of z minus n, which is equal to e the power minus n, this will tends to 0 as n tends to infinity. Right? Alright, this is just a small remark for your understanding. So next time I will be doing a fundamental theorem of algebra and their corollaries. So just keep watching my videos and subscribe my channel for latest videos. And if you need my course Real Analysis, then you can check the description box. The link is provided over there. Thank you for watching this video. Goodbye. Have a nice day.